Hello, I'm delighted to have this opportunity to share my work with you through the internet. I am a graduate student from Beihang University in China. The title of my presentation is Multifunctional Smart Skin for Multidimensional Perception for Humanoid Robots. I will talk about the design of an artificial smart skin that supports multiple functions. First of all, my research is conducted in the background of humanoid robots. To enable the robots to provide advanced services, using human skin-inspired smart skin is a feasible way for them to interact with users and perceive environmental stimuli. A variety of techniques have been proposed in recent years to enable robots to sense physical changes, such as pressure and temperature. However, most of the reported works focus on single-dimensional sensing, especially the pressure or touch sensing. In order to achieve more detection functions, some work try to stack up layers of different functionalities. For example, humidity, temperature, and pressure sensing layers are stacked in this work. However, this process increases the front-end and security complexity, as well as the system power consumption and component costs, especially when a large area is required. So its use in the commercial products is limited. Therefore, the highly desired attributes for smart skin in the foreseeable future should be multifunctional, simple structured, and low cost. To demonstrate this possible development trend, we develop a three-layer structure for multidimensional sensing, with an upper polyimide film, a copper electrodes layer, and a PVDF film, with the dielectric property of polyimide layer and the piezoelectricity of the PVDF layer. The device is able to detect touch position, the finger proximity, the dynamic force, and the environment humidity. This simple structured device only consists of commercialized materials and does not require clean room fabrication conditions, so it potentially allowing massive production. Then I will explain its working principles, the system construction, the signal processing methods, and the corresponding results. This slide shows the device architecture and the working principle. The four functions are realized by mutual capacitive effect and piezoelectric effect. First, here, the interdigital copper electrodes are fabricated on a polyimide film to form mutual capacitors in a single layer. The upper and the lower films serve as the dielectric medium. When a human finger approaches or touches the device surface, the electric field is transformed. Therefore, touch events and hover distance can be recognized by the capacitance changes. The top polyimide film has the multi-hole structures, and it serves as the humidity sensing material. When it absorbs moisture, its permittivity will increase, and thus increasing the mutual capacitance value. These three types of signals can be further differentiated by a following processing algorithm. Then, to capture force events, the piezoelectric-based technique is selected due to its passive converting ability, which will enable lower power consumption. And PVDF film is chosen because of its high flexibility and high piezoelectric coefficients. The generated charges are collected by the copper electrodes. The capacitance signal and the piezoelectric signal are read in turn by a time-sharing circuit. As shown in the lower left picture, the electrodes are arranged as a 6 by 6 array, and area of each element is 5 by 5 square millimeters. A practical image of two electrode pairs is given. The geometric dimensions are provided here, and the subfingers are introduced to increase the mutual capacitance value. The system construction is demonstrated here. In force or hover touch experiments, both capacitive and force information are obtained and uploaded to an upper computer. Through a subsequent algorithm, the signals are further separated and processed to be the force distribution, the 2D position, hover distance, and humidity. Block diagram of the radar circuit is shown on the right. The capacitance and force signals are read by turns under the control of an either-or circuit. The capacitive information is processed by capacitance to digital converters, and force signals are transformed into voltage amplitudes by charge amplifiers and analog to digital converters. After that, the transformed digital messages are conveyed to the microprocessor unit through an I2C bus and transmitted to the host computer via Bluetooth. The capacitance and force sampling rates are 80 and 200 Hz respectively for the 36 points. This slide shows the algorithm for calculating humidity, hover distance, and position from the obtained capacitance signals. Firstly, the relative humidity is calculated by time and space filtering methods. Based on the fact that the environmental humidity occupies low frequency band, a low-pass filter is applied first. Then, the gradient of the capacitance matrix is used to determine if there is a hover or touching event. By removing the points that are affected by human finger and find the average, the capacitance offset is obtained. The offset serves as the baseline for contact and hover touch detection. These two situations are further determined by comparing the maximum change with a hover event threshold. The hover distance and relative humidity value are obtained by pre-fitting results. If there is a touch event, the closest sensor is found first, and this distance between the touch point is calculated using the Gaussian position estimation. This slide shows the device testing results. The overall mutual capacitance offset is measured first because it is virtual to the determination of touch and hover event. As the left figure shows, average capacitance offset is 0.8 picofarad with good uniformity. The capacitance change with different hover distance and relative humidity is then examined. In touching tests, the mutual capacitance change shows pro-potential relationship with finger proximity in a range of 0 to 2 centimeters. The finger touch induced capacitance change is presented here. Half of it is therefore set as the touch detection threshold. The red picture shows the humidity testing results, indicating a high humidity responsivity. For dynamic force sensing, the charges collected by each electrode pairs are calculated by this formula. Here, F is the external force and D is the piezoelectric coefficient of the PVDF film. These two coefficients represent that 1/3 of the charges on a single side are collected. The left picture shows the force sensing responsivity and sensitivity of the 36 sensor array. Then the system performance is examined. The results are summarized in the right table. The force responsivity is increased due to the radar circuit's amplification. This lower right picture is an example of the testing result in touch experiments. The spatial resolution is tested to be 0.2 millimeter. To conclude, the results shows that this technique successfully achieves desired attributes. Compared with works in the literature, the force sensing responsivity here is lower because the electrode layer collects only one side and one-third of the generated charges. However, as talked above, this design offers more sensing functions in a single structure. The proximity sensing range is limited to 1.7 centimeters, which needs further design to improve its mutual capacitance value. And in the present work, the effect of the rest of hand and the touch event at the device boundary is not taken into consideration. In our future work, we will optimize the electrode structure to increase the force responsivity and capacitance offset, and we will apply it to various scenarios of human-machine interaction. This work is funded by the China National Natural Science Foundation and Beihang University. That's all. Thanks for your watching.